we're going to talk about encoding text with BERT, and I say I was very happy to get these projects up here because it helped me understand more about how large language models work. And as you know, large language models are the thing getting the most attention about artificial intelligence. Certainly not the only thing it can do, but the one people care about the most. And so the one thing that really puzzled me about large language models is how does it understand the meaning of the words? It doesn't really understand the meaning of the sentence, but it does understand what synonyms are. It knows if two words mean the same thing or they mean different things. And I wondered how that's even possible. My first thought is they had to pay humans to like rank words according to some standard, but that's not how they do it at all. Here's how they do it. You break the sentences, you have some training data, typically an incredible amount of training data, like practically all the sentences they could find on the internet, just billions of sentences and paragraphs and pages of stuff written by humans. Although, I should comment, that is a huge problem. More than half of the data on the internet is now written by large language models. So you're training on data that is in fact corrupted by inclusion of data written by machines and not by humans. So a huge bottleneck in the future is where you're going to get a large bunch of data written by humans. And this is why companies like Twitter claim that they have an enormously valuable property because they have all those tweets that are supposedly written by humans, although most of them have been written by bots for years. So in all cases, you've got a serious problem. But anyway, you have some training data, which you hope is an example of good writing. Then you turn it into, you can tokenize it, you turn it into numbers. And you can use a variety of systems here. The simplest one is just to have one token per word. Let me just try zooming in this way because there. Okay. So here you have Napoleon revolutionized military organization. You just assign an arbitrary number to each word. Then you have a token for the start of a sentence, the CLS. Then, this is the part that always struck me as magic. You now embed it. And in the case of BERT, one common one, you embed each word into a 768 dimensional vector. And those vectors are meaningful in the sense that similar words will have similar vectors and words with similar meaning differences will have similar vector differences. So you have actually mapped the meaning of English words into a meaningful representation of numbers. And that is what seemed like magic to me. And this is how it works. So here you tokenize three sentences. Napoleon revolutionized military organization. Napoleon has legacy. Legacy still lives. Those are three sentences. So here's the words. Now you tokenize them, and here they are showing as tokens. All you're doing is assigning numerical values to them, and those numerical values are essentially random. They don't mean much of anything except that they stick with it. Napoleon has 8891, and when Napoleon occurs again, it's 8891. Legacy is 8027, and here it's 8027. The period is 1012 every time, so you've just turned the words into numbers. So far, we haven't really accomplished much of anything. We've also added beginning and end to it. Right, so now we do masking. What BERT does is you mask some portion of the words, 15% of the tokens randomly. So 15% of the tokens you turn into this mask number 103. So now you get this. Masked, these three ones have been turned into 103. So you don't know what word goes there. And now this is a very common trick, and this is also how Stable Diffusion works. You start with unlabeled data, like photographs you find on the web. Then you want to turn it into labeled data so you can train your model. So you remove part of it, you know what you removed, and now you make your model guess at what part you removed. So you remove some tokens, some words randomly, and then you get the model to try to guess from the context what word goes in there. And then you train it to guess accurately what word goes in there because you know what the right answer is, so you can train it. This is how you do it. So it tries to predict the masked word. So here we have a sentence, artificial intelligence mask take over the world. There's a sentence with a word missing, and after training the model, it will attempt to predict that word, and here's what it does. It says there's a 20, can has a 31% chance, artificial intelligence can take over the world, or artificial intelligence will take over the world. The will has an 18% chance of being the right word. To take over the world, that would be part of a sentence. That has a 5% chance, and the next one has 4.5%, and so on. That's what it means. It gets pretty good at filling in the missing word from context. So this means your model and its representation are accurate enough to make a sentence sound good. The words will be the word that does fit in that sentence in the context of the words near it. And it does all this without knowing what any of them mean. It doesn't know the absolute meaning of any word, but it does know the relative meanings of words, which is how likely is this word to appear next to other words. So it can figure out which word is most likely going to fill in. That will make a sentence sound good. And the next thing is to make larger structures than sentences sound good. And here, all you do is you use pairs of sentences. Napoleon has legacy, legacy still lives. You take pairs of sentences out of your data set, A and B, and half the time you replace sentence B with a random different sentence. And the other half of the time you leave it alone, and you train the model to tell whether this sentence is in order or not in order. It's exactly like the previous one. Even though it doesn't understand the sentences, it learns what sentences should be near each other in context. And this will make the paragraph sound good. The structure of sentences following each other will be as expected. Now, notice it's not actually understanding anything or conveying any meaning. What it's doing is imitating humans. It's finding a way to fill in sentences. Now, I once saw a book called The Romance Writer's Phrasebook. I knew someone who was trying to write fiction. And if you write normal fiction and take college classes in it, they will tell you have to not repeat other people's work, you have to be original, you have to write what you know. But if you're writing genre fiction like romances, you must do the exact opposite. People that buy romances, they all look the same, there's hundreds of them, they buy them and read them fast, they expect to see familiar words and familiar phrases in there. And they even tell you, you have to not deviate from the pattern. If you do, your book will not be popular. I saw a movie called No Country for Old Men that looks like a Western, and it is absolutely not a Western. The hero doesn't win, it's not at all what you think, and the audience was disgusted. There was like screams of protest when I saw this movie, because people expected to see an ordinary good guy versus bad guy shoot 'em up Western, and it totally is not that. But it looks a little bit like that. So you think you're going to see the standard story, and if people don't see what they expect, they will get mad. And that's the consumers of romance novels do not want to see originality and new stuff. They want to see it's like watching a TV show. You want to see an episode where the stuff you expect will happen. And so that's what's going on here. It's not able to express anything new. It's just imitating what humans do. And that's why people say if you use this to write an essay for like a college course, the teachers say they can easily catch you because you don't actually say anything or make any points. You just sort of babble in a sort of way, saying sort of what you expect to see next. So anyway, but that's what it's doing. Now after this, it's going to learn how to put sentences in an order so they will look good, and words in an order so they will look good, without ever understanding anything. That's how it works. So you can code these things, and then you can try having it do some jobs. So here's the code that does it. I guess I'm not going to bother doing it live today. You can run this thing and get some tokens and see the tokens going in here. And then you can test it on sentiment analysis, which is a popular thing and what I was also talking about in the news. This is one thing LLMs are pretty good at. If you want to see, you have movie reviews that will be like a whole page of text, and you want to boil it down to like good or bad or something. So, and you download some movie reviews and you get them with the number of stars, which is the summary of good or bad. So you have effectively labeled training data. You have a bunch of text and you know with the number of stars whether they thought it was good or bad. So you can see, can my LLM read that text and predict whether the movie is good or bad? And that's what you have here. So here's some data without a sentiment. Here's the original data. Here's the start of these sentences, and here's the sentiment, positive and negative. Or what you've done is it came with a rating of 5 stars. So in this case, you turn the 5 stars into good or bad. I think I forget how you did that, but maybe positive or negative. And so now without the sentiment, you have this, and you want to predict this. So BERT can do it. You run it through here, and you predict the sentiment. It's going to have a training. You train it. You have pre-trained BERT, which will just turn the words into tokens and into high-dimensional vectors, the way it's previously been trained on a large segment of English words, and then it's going to classify them for uncased sentiment. This is something that's already been programmed by somebody else to classify things as a positive or negative sentiment based on all the words in there. So you can run this thing and see how well it's accurate. So we're going to say if the sentiment is 1 or 2, which is 1 or 2 stars, that's bad. And so if it calls it positive, that's an error. If it calls it bad, but the sentiment is 4 or 5, then that's a flaw too. If the sentiment is 3, I'm not going to count either result as bad because 3 stars is the middle. So that's the game. So now I can predict how many are going to be wrong. And so you see it got 6 wrong out of 100 movies. So it's pretty successful at determining the sentiment of a block of text. All right, and that's all I wanted to show you today for this BERT one. We'll play with these a lot more later, but that shows the task that came up in the news today, sentiment analysis, and this is also what the military wants. The CIA wants to do this to analyze a diverse amount of data from many sources, boil it down, and tell me a fact, like, is an attack coming from Al-Qaeda next week? Take all these facts and add them up and tell me how likely do you think that is to happen, which is the thing human analysts would do, but AI will help them do it, presumably handle a large amount of data more effectively. And this reminds me of pen testers. Pen testers run scanning tools like Nessus that send millions of requests to a server and see if it finds a flaw, but they also do manual testing because the tool can only do a certain amount of tests. But the tool has an advantage. It really goes to every single page and clicks on every link and fills in every form, whereas the human might not. So the tool gives you some automated analysis, but you also do human review, and using the two together is where you get the best results. The disasters I hear about are mostly from like police departments that trusted the AI and did not do any other research to back it up. You have to understand it's not a very perfect tool, and it may be of some value, but it can also be wrong. So anyway, that's the one I wanted to show you today. I see no comments in the Twitch. I'll stop the recording.